Thank you for the introduction. And this is a topic I think should make you think a little bit, because it plays a very important role in what I call propaganda. And it took a while to understand this. Propaganda works, and I give an example here, but Laszlo gave me a better example, really. It's effective. It makes people think a certain way, even if that way is irrational. So, for instance, the example I gave was a gentleman who is actually very much against what is called net zero, bringing emissions to zero. And yet he felt it essential to say he's not a climate denier. That, he's not saying that, he's saying it'll get warmer and it should be a policy to reduce the effects of CO2 as soon as possible. Why does he feel the need to say this? He doesn't understand the problem. He's against the policy, but he's been told it often enough. Now, essentially, Joseph Goebbels, who is an expert in propaganda, after all, he got millions of Germans to believe so many things that they behaved like animals. He said, if you tell a big enough lie and repeat it endlessly, it becomes truth. And people notice the repetition. But in fact, the point of it being big enough is crucial. If you tell a little lie, it gives a target to be attacked and it ends. But if you tell a very big lie does everything wrong about it, then it's a hard target and people absorb it. One of the things that's crucial is people don't know about science, even educated people. And so if they're told all scientists agree and if it's too complicated to follow, they're happy to follow. And so, you have Orban, who is in many ways rational, but he feels one cannot deny the science. What he doesn't understand is science is a very strange word. It's the only word I know of where if you put the in front of the science, it becomes the opposite of science. And this is one of the problems we're dealing with. At any rate, let's consider all the things wrong with this narrative. And we'll begin with the question, what is climate? And what you have so far is people present you with a metric. We're going to discuss this. It's a global average of temperature deviations from 30-year means. And the claim is this is controlled by CO2. Now, people have accepted this with ease. And I would argue that none of this makes any sense at all. Let's look at what the World Meteorological Organization refers to as climate. They have a very arbitrary definition. They define climate as the behavior of 30-year means. It's essentially a low-pass filter. And it's just a definition that's meant to distinguish climate from weather. Weather will be short period and long period trends we'll call climate. It makes no claim at all for globality. Now, there's something about taking an average over the whole globe which appeals to people, but it makes no sense for this. Let's see why. Here is what people before climate alarm were studying when they studied climate. The biggest problem we were confronted with was to understand today's climate. And so one approach was the Köppen-Geiger classification. And they took the whole globe and divided it into different climate regimes. And as you see, there are a great many regimes. The climate, as you know, of different areas, West Coast, East Coast, so on, are all very different. And we're sort of arguing now that each of these dozens of regimes acts together according to CO2. We know that's not true. In reality, there is little correlation between local 30-year means and global average. We'll see this again several times. So here is what we currently politically define as climate. You have this graph. You see that it is slowly increasing from 1850, and then it's shooting up after 1950, 1960. And you're accustomed to looking at graphs like that and saying something's increasing. You're not so accustomed to looking at the axes, because all you're looking at is 1 degree. It's pretty small. And you're showing the results from various institutions that are calculated. They get roughly the same thing. But, you know, what are you looking at? Well, you're not looking at the average temperature. That makes no sense. You don't average Mount Everest and the Dead Sea. What you do is average the temperature change. You take the deviations from 30-year averages and you average those. And you get a little bit more than 1 degree over 175 years. And you're told by international bureaucrats like Antonio Guterres that another ½ degree and it's the end. Where did he get this from? And this is one of the complaints I've had. You know, the UN has the Intergovernmental Panel on Climate Change. And the working group 1 is the science report. They never say this. They never make this claim. The United States has national reports on climate. And they're biased. There's no question they're biased. But they never make this claim. So, you know, the political claims are simply meant to frighten the public into compliance with absurd policies. And, you know, it's always been a puzzle to me why people would be frightened of a warming that is much smaller than the temperature change that all of us adjust to between breakfast and lunch. How many people between breakfast and lunch say this has been very difficult to adjust to? And I've never met anyone like that. But we're told this is what we should be afraid of. There's an interesting aspect to this, and you see this in the US, in France, and elsewhere, I'm sure. Ordinary people realize this. French farmers, when told, you know, they have to kill their cattle and so on, they realize this is silly. But the educated elite, I fear, are accustomed as they are to pleasing their professors, they will rationalize anything. And so you have something where I think common sense says, this is ridiculous, but we have people trained to believe such things. It's a bit of a problem, but here is something that clarifies the puzzling aspect of it. We're including the data points. So now you have the data from which you got the curve you saw before, the rise. But what you see with the data is that the data points densely cover a range of about 16 degrees centigrade. And this is an order of magnitude, more than an order of magnitude greater than the change in the mean. So you have the old problem that everyone doing experimental work, when you're looking at the small difference of large numbers, it's unreliable. And what you really have here is a statement that essentially, I think, at any given time, almost as many stations are cooling as are warming. And in fact, if you plot, I won't go over this much, but the correlation of 30-year running means is all over the place when you try and correlate it with the global mean. And it looks pretty random. And in fact, it turns out the weighting is such that it tends to prefer the cooling. In any event, the insistence on globality leads to some bizarre absurdities. And one of these is an issue that was very important at the beginning of the UN's Intergovernmental Panel on Climate Change. And that was the medieval warm period. One of the pioneers in historical climatology was a man called Hubert Lamb. He founded the climate department at the University of East Anglia, and it's played a big role in this subject. And using numerous historical records, he made a pretty convincing demonstration that in the Middle Ages, for several centuries, Europe was unusually warm. This was, prayers for rain and growth of different plants and so on and so forth, wine growing. And at the beginning of this climate alarm, people were saying, well, warming is not unusual. There's the medieval warm period. And so word went out throughout the community, at least as far as I could tell, how do we get rid of the medieval warm period? It's an interesting goal to get rid of a historical period. And there were several attempts, and all the attempts did the following. They tried to argue that the warming was only in Europe, and the rest of the world compensated for it, so that the metric you saw of global mean temperature anomaly did not show a peak. And you had people doing all sorts of things, and the most notorious was a guy called Michael Mann, and he used only a few handfuls of bristlecone pine trees and looked at the tree rings, which mostly respond to moisture, not temperature, put arbitrary weighting on the different trees, and got what was called his hockey stick, which was something that showed nothing happening for 1,000 years, and then it goes up in the last 100 years. And it was a way of saying, even though the change was small, it was unprecedented. Now, somebody checked his work, and they found if you put in random numbers, still gave you the hockey stick. And, there are all sorts of things wrong. And it caused a lot of excitement, in a sense. So there were 2 investigations made of his methodology, one by the American Congress and the other by the National Academy of Sciences. And both of them concluded that his methodology could not be used to infer anything about the medieval war period. Didn't matter. He received numerous awards and he was elected to the National Academy, where his supporters lied about these reports. It's interesting, for all of us who participated in the 3rd assessment, which received a Nobel Peace Prize, we got this certificate here that said that we had contributed to a Nobel Peace Prize. I keep this one in one of our bathrooms, it's sort of amusing. But at any rate, Michael Mann, despite the warning that this did not mean that we had been awarded the Nobel Peace Prize, for quite a while he listed himself as a Nobel Prize winner. In any event, what this disguises is that what is truly bizarre about his work is not the statistics, but that it assumes that several centuries of anomalous warmth in Europe and presumably several centuries of anomalous cold elsewhere on Earth did not constitute climate change. What does climate change mean if you reject major changes? And I think that's often missed in all this discussion of the statistics. Now, what I'd like to briefly go through, and I hopefully finish, and don't worry about too much of the details, but the question is, what do we know about climate change, really? And what we do know is that the fluctuations are mostly local and extratropical. And what is not realized, and I think this may, hopefully there are some questions, if you go poleward of 30 degrees latitude, radiative imbalance is not a significant causal factor. The temperature difference is determined by the dynamics, and the radiation adjusts to it. Of course you need a balance, but it's not causal. What then causes local climate change? And here you have a lot of things going on. And we'll talk about a few of them, but you should remember that the surface of the Earth and space do not constitute a closed system. The ocean is always changing the balance at the surface. You have ocean circulations that have time scales between the El Nino cycles, which are a couple of years, 4 years, and 1,000 years for some overturning circulations. And as they take heat away from the surface or bring heat to the surface, the climate in that neighborhood will be affected. There is also the problem is oceanography is not at a state yet where one understands all these circulations. The attention has been devoted mostly to the very large scales. So we have a broad idea of the wind-driven circulations in the Gulf Stream, the thermohaline circulations on a global scale, but regional differences in the highly topographical ocean, we have not even begun to study in detail. So that's one source. The business of tropics versus mid-latitudes. Here is a schematic illustration, and we'll come back to it several times. Between the equator and 30 degrees, you have a dominant Hadley cell, which is ironing out temperature differences. But as you go poleward, you have weather systems. When you look at the weather map, you see the highs and low pressure systems. They are traveling from west to east, changing the weather as they go. These are convective instabilities, and we'll come back to that. They determine the temperature difference between the tropics and the pole to a very large extent. We'll see why you have this difference, but it's only in the Hadley circulation that the greenhouse picture is relevant. Okay, why do you have such difference? By the way, I mean, in mid-latitudes, your prevailing winds, the mean winds, are from where? They're from west to east. What about the tropics? They're from east to west. The winds literally change. The tropopause, where the temperature decrease ends, is about 16 kilometers in the tropics. As soon as you move poleward of the jet stream, at the edge of this, it sinks to 12 kilometers. The physics keeps changing as you cross that boundary. Let's see. Now, we're talking in the first thing with the ocean when we're talking about things that are 1,000 years, 4 years, 30 years, so on. There, I think the oceans are relevant, but the big changes that geologists come up with in their data are, of course, the glacial maxima, where for the last 700,000 years, roughly with a dominant period of 100,000 years, you have ice ages. And then the Eocene, 50 million years ago, the record looks as though you had a much warmer climate with alligator-like creatures in Spitsbergen. The tectonics was not so different, so the layout of the continents was roughly the same. What's going on there? And essentially, the changes that are occurring in these major changes are primarily changes in the temperature between the tropics and the pole. During the glacial maximum, it was about 60 degrees, 20 degrees more than today. During the Eocene, it was only 20 degrees. Again, 20 degrees different from today. Today it's about 40 degrees. So let's see what the implications of that are. Okay, this is a rough diagram. I mean, you know, if we're going to take the Greek letter phi to be latitude, X is the sign of the latitude, so it's the area weighting. X equals a half is 30 degrees. Sine of 30 degrees is 0.5. So the change in the mean temperature of the Earth is going to be the change in T1, which is the tropical temperature, and this is rough schematic. And then it's going to be minus 1/4 of the change in temperature between the tropics and the pole. And, you know, it's 1/4, as I'll mention, somewhere around here, because, you know, it's half the Earth, and the mean is half of delta T2. So it's 1/4. Now, what this means is that those major changes, the Eocene and the glacial maximum, represent a change in the mean of only 5 degrees. Now, what's happened is you have people who are trying to promote the alarm, so they're introducing, quote, positive feedbacks to change it from 1 degree for CO2 to 2 degrees or 3 degrees or 1.5 degrees and so on. And they are arguing that when you start getting 3 degrees, 4 degrees, you're getting close to what you had with major climate change. So maybe there's something dangerous going on. Now, the trouble with that is that you have this business of delta T1. If delta T2 is 0, delta T1 and delta T are the same, and a 2 degree change or a 1 degree change is a 1 degree change. It's not 20 degrees of the equator. Well, let's think about that a little bit. Okay, here is an explanation of what's going on. And probably the order is a little bit peculiar, but what the alarmists are arguing is that the big change in the tropics-to-pole is an amplification of what goes on in the tropics. In the theory of present climate that we have from hydrodynamics, there's no such mechanism. There's no physical mechanism that says you amplify what's going on in the tropics. You get independently the gradient in the extratropics, and then the tropics is like an integration constant. Why does the Earth behave that way? And it has to do with the Earth's rotation. When you have rotation, you have a Coriolis force. And the Coriolis force is important for the vertical component of the rotation vector. So if you're poleward of 30 degrees, the projection of the rotation vector is mostly vertical. And if you're toward the equator from 30 degrees on either side, the projection is mostly parallel to the surface. So in the extratropics, it inhibits cross-isobar motion. In other words, if you look at a weather map, the curious feature is the motion is not from high pressure to low pressure, but rather parallel to the isobars. Any engineer looking at pipe flow would find this a little bit strange. On the other hand, when you go to the tropics, the flow is from high to low pressure and irons out the pressure gradients and the temperature gradients. So you get very different physics. Now, the interesting thing about the hypothesis of polar amplification is it is testable. And this is quite remarkable that almost no one tested it. I mean, I wouldn't worry about this. A picture of what happens non-schematically. So the dotted lines are what are called potential temperature. Potential temperature is a measure of entropy, but what it amounts to is if you take a parcel of air from a given height with a given potential temperature, it will achieve that temperature if you bring it to the pressure at the surface. Technicality, these occur all the time. And then there is something called vorticity, potential vorticity. And that is something that is conserved in the extratropics. But in any event, the picture you see, and you see here, the temperatures are pretty flat, and then they go up, and essentially you have something funny going on in the tropics, the polar region, excuse me. Now, what happens is we can look at this, and let's see what the next, what you can do with the data is look at the equator to pole temperature difference from about 1880 to the present. And if you look at this graph, I mean, look at the scale, and there's almost no change at all since 1880 to the present. On the other hand, if you look at the global mean and the tropical mean, they're almost identical. So we see in the data, there is, in the present warming, no polar amplification, at least not anything statistically significant. Now, okay, so I go down here. Let's summarize. I think that's the next one, is it? Yeah. What we have here. So major climate change, as opposed to the shorter term stuff, like 1,000 years, is due to profound change in the tropics to pole temperature difference. Now, we see this leads to relatively small changes in the global mean temperature because it involves only half the Earth and half the temperature change involved in delta T2. So it doesn't look big in the mean. The changes in the tropic to pole temperature difference are almost totally due to extratropical processes like the instabilities responsible for weather systems or snow ice cover. I'll come back to that in a moment, because that involves something called convective adjustment. Have any of you heard of that term? Well, the easiest way to see it is when you have heat transport by fluid motion. There comes a point where it eliminates enough of a gradient that the instability growth rate goes to 0. And it tends to bring the flow to that state. Okay, and we can calculate what the limit is for saturating the transport of heat by the highs and lows of weather. So we'll come to that in a moment. Anyway, this is simply saying what is at issue. And climate alarm assumes that, in contrast to 3, polar temperature change is simply an amplification of changes in tropical temperature. But the observations show that warming since the 19th century involves essentially no polar amplification. And this means that small changes in tropical temperature are associated with small temperature changes everywhere. So the common sense interpretation that if you have global warming of a degree or 2 or even 3, and that's small, is correct. It is not associated with amplification at the poles. The fact that the IPC, and this will come to in a moment, models display significant changes in tropics to pole temperature difference, contrary to the data, simply means that the models are wrong. And we're seeing it time and again. People are saying, we're going to test this by running the models. And you can't test a model with a model that is wrong. And here you have ample evidence that they're getting the wrong answer. Here's the results. We took a sample, but it's true for the full set of IPCC models. So on the left, you have the rate of warming in the polar cap, 30 to 90 degrees, relative to 30 degrees tropical, for a variety of models, and at the far right you have the observations. the observations are tiny and statistically insignificant. Almost every model is giving you much more. On the right, you have more detailed information. You have the change in the tropical temperature from the data at the bottom, and you have the polar cap, the delta T2 in the column there, 0.01. And then you have the values for the various models. And it turns out that the Intergovernmental Panel on Climate Change models show not only polar amplification, which the data does not show, but they also show too much tropical warming relative to the data. There are large variations among all the models. Some of the models have sensitivity to a doubling of CO2 of almost 5 degrees or 5.6. That's the British ones. They're really out of whack. But you have other models, including one from Russia, which are a little bit more sensible. I mean, that gives you 1.8 is the sensitivity. But all of them are in definite contrast with the data. The interesting thing about that, though, is that all the models differ from the data in only one direction. And that's worth paying some attention to. They all make it warmer than the data. Okay, let's go to the next. Yeah, the models all run hot. And again, I hope this isn't too complicated a picture, but essentially what you have is the colored dots are the various models, and this is height. And it's 1,000 millibars and 100 millibars. Meteorologists usually use pressure instead of height. And the temperature is giving you this behavior. It has a maximum somewhere around, this is around 300, 200 millibars. And they tune it so that you're not too out of whack at the surface. But as you go up higher and higher, the discrepancy gets bigger and bigger, that the models are running too hot. That shouldn't be surprising. This is something, I mean, I've discussed it with people running models at various labs, and they've admitted that if they get runs that don't show warming, they throw them away. I mean, the fact that you can have these large range of errors, but they're always in one direction, is not entirely natural. In any event, here's the point, we've made it before. Without polar amplification, we only have delta T1, which is small even with highly unlikely positive feedbacks. Now, that's important because, I mentioned you want a big lie. And so what happened was, when they started showing these positive feedbacks, I don't know how many people here have heard something called Le Chatelier's principle. And this is an interesting principle because it's never been proven, but it argues that nature tries to prevent change. And here we're told nature tries to take whatever you do and make it worse. That goes against most thinking about how nature works, but okay, I could go through the history of how they found that, but it still doesn't make it very likely. What happened was two people, Manabe and Weatherall. I should have mentioned Manabe got a Nobel Prize in Physics for this. using a completely unrealistic one-dimensional model of the atmosphere and assuming that relative humidity remained constant, was able to double the response to a doubling of CO2. And that actually got people excited, but there are a couple of reasons to suppose that the feedbacks really are negative. And apart from explicit measurements, there are a couple of features that are worth paying attention to. One was something, do people know the name Carl Sagan?
Yes.
Yeah. He and a colleague wrote a paper in the 70s, 1972, presenting what they called the early faint sun paradox. And the paradox was the following: if you take current models of sun-like stars, then of course they are getting hotter with time. And so going back 2.5 billion years, the solar output was estimated to be 30% less than today. Now remember, when we're talking about carbon dioxide doubling, we're talking about 1 or 2% change in the radiative power. It's 30%, much bigger. And yet the geological evidence was that the oceans were there, they were not frozen, and they were similar to today. How is this possible? And there's a whole mini industry trying to say maybe you had tons of CO2, maybe you had this, that, and the other. But the truth of the matter is there are negative feedbacks that easily accommodate that instead of positive. There is another thing left out of all the estimates of feedbacks, and that is the fact that if your changes between the Eocene and the last glacial maximum involve changes in the temperature difference between the tropics and the pole, they are going to affect the heat flux taken from the tropics to keep the poles warmer than they would be in radiative equilibrium. Remember, if you did not have transport, the poles would be still colder than they are today, much colder. They are the present relative warmth because heat has been carried from the tropics to the pole. The fact that you have these changes in flux without significant changes in tropical temperature, again suggests that the tropics are actually quite stable. Anyway, that was the focus of a lot of attention. And again, this is the business of the big lie. You see, the feedbacks and you start worrying about them. But in many ways, this was, again, a distraction from trying to figure out how the whole system worked, with the polar transports, the extratropical transports, and so on. In any event, given what we now know, suggesting that climate is an existential threat is, I would argue, both malicious and stupid. Agreeing with such suggestion maybe is only stupid, but in this case that's bad enough. It's causing immense danger. Danger is changes. Now, before ending this talk, I'd like to return a little bit to real climate changes. And, so the question is, what here should you look at if you wanted to study this further? And as I mentioned, there is something called saturation. I don't have that little arrow again. It turns out that if you do the instability calculation, it's a hard mathematical problem. And there's a paper in 2013 by a young scientist, Malte Janssen, and Raffaele Ferrari at MIT, that showed that what the instabilities try to do is establish the slope of the last isentrope leaving the tropics and defining the tropopause, the end of the decreasing temperature at the pole. And that in turn determines the temperature difference at the tropopause at the pole between the tropics and the pole. And it sets it at about 20 degrees. The interesting thing about that is the measurements, the data, show that at present that is the temperature difference that we have. It's about 20 degrees. That's an important success for the theory of the saturation of the instabilities. The question is, why are the surface temperature differences bigger? And what I point to is, if you look at the polar region, you see that things are breaking down. There's something funny going on there. And what's funny going there is something called Arctic inversion. And what's happening is, you know, for instance, if you send a balloon up here, the temperature is decreasing with height. That is not true over snow and ice. Over snow and ice, you have the inversion, where the temperature, instead of going down, is going up for about 4 kilometers. And as a result, the temperature difference, tropics to pole, at the surface is greater than it is at the tropopause. So we have some idea of how it's working, but the amount of research on the Arctic inversion is pretty small. Only about a handful of papers since 1932. And there are a number of problems that would still exist with that. Let me go, where again? Okay. So there are some of the problems. The issue of what causes the ice ages, in terms of existing problems. Milankovic has a paper, he's a Serbian, I wouldn't call him a meteorologist, but he argued that the glaciation cycles of the last 700,000 years, he didn't know that, were due to orbital variations of the Earth, changes in the obliquity, the precession of the equinoxes, the eccentricity. And his work turns out to have been conducted largely in the Hungarian Academy's library. I mean, Laszlo sent me something on this, and passed during World War I. And it was supplemented by work of a Hungarian scientist, Vaksa, I don't know the pronunciation. But the interesting thing is knowledge of this was largely lost. And there was a large program in the US and internationally called CLIMAP. And the purpose of it was to understand the last glacial maximum. And so they were looking at Milankovic's theory. And the reason I mention this is his theory is vindicated. But the geologists working on this did not conclude that. What they did was, and these were distinguished people and good scientists by and large, but not specialists in this sort of thing. And so what the climate program found was when they looked at the power spectrum of the ice volume during the glaciation cycles and compared it with the Milankovic parameter, which essentially is the radiation, the incoming radiation at 60 degrees latitude in June. And the reason for that was very reasonable. He was saying, it's snowing every winter, but whether that snow survives the summer depends on the amount of sunlight reaching the Arctic in summer. And that varies by 100 watts per meter squared over the orbital variations. which is huge compared to the 1% due to CO2 or something. In any event, they found that in the power spectrum, they had similar lines in the ice volume and in the Milankovitch parameter, but there was disagreement in detail. And then a couple of young scientists, one former student of mine, Jerry Rowe, and before him, some young Swedish astronomers, Edvards and Vidal, 2002, realized that there was an error in the climate thinking. What was the error? They were comparing the power spectrum of the ice volume rather than the power spectrum of the time rate of change of the ice volume. So these young people corrected that, and then Milankovitch looked perfect. So I think at this point, it's an excellent theory for the glacial maximum. But there are still outstanding problems. So for instance, it's true for the last 700,000 years, but there have been a few million years of ice ages, and before 700,000 years, the dominant period was the obliquity cycles, 41,000 years. And the question is, why is that? And that's still open. It's a reasonably good question. I think I know the answer, but at my age, I'm not going to work it out. And then there is also the fact that the Eocene does seem to be 20 degrees equator to pole, which we see at the tropopause, at the north, at the polar tropopause. And that's fine, but there are other periods that seem to be ice-free, where the temperature difference is not 20 degrees. The question is, why is that? And there are all sorts of questions that exist. But, and I think this is the important thing, there's plenty of work before we have a solid understanding of climate change on the Earth. But I would argue that we are at a point where we can at least sketch out a rational agenda. And we're certainly at a point where we can stop confusing climate change on the Earth with climate differences among different planets, which is a very different problem. And I think, to conclude, future generations will be quite puzzled. They'll marvel at the fact that this confusion between two versions of climate for the Earth and climate changes for different planets, was used to justify the destruction of Western industry, demand that billions of poor remain poor, prevent the use of fertilizer, thus perpetuating hunger, cause the slaughter of cattle, and numerous other displays of societal insanity. With that, I leave you. Thank you for your attention. Questions?
Yeah, thank you so much, Professor Lindzen. No, first I would like to ask the colleagues here in Sopron whether they have any question to Professor Lindzen.
Yes, so you have argued that the melting of the polar ice caps wasn't because of the climate change, but I didn't make sense for me why the poles are melting. For example,
the glaciers are melting as well, not just the ice on the poles.
The answer is, in some ways, I don't know. I don't know why the glaciers came. For instance, in the medieval warm period, there were almost no alpine glaciers in Europe. Then came the subsequent cold period after, the terrible 14th century and subsequent centuries until 1800 roughly, when glaciers were advancing. And you have all sorts of literature of people saying their village has been overrun by a glacier. And then somewhere around 1800, before CO2 had any importance, glaciers have started to retreat. And in some places they've stopped retreating. But you know, how shall I put it? One of the things you learn is correlation is not causation, right? So for instance, you have people, and I see people awarded for saying, since 1800, CO2 has gone up and temperature has gone up. What else do you need to know? Well, since then, population has gone up, income has gone up, life expectancy has gone up. Are all of those causal? No. And so, you know, nature has lots of things going on. I can't answer that, but I don't know why the glaciers even came.
Okay.
Any more questions here in the room?
So, Professor, when I talk about these things to my wife, and I say that I'm dubious about CO2 causing all this, she always asks me, okay, then tell me what causes that.
And that's an important trap.
Yeah.
Because, you know, you have all sorts of people, well-meaning, who are saying, it's not CO2, it's the sun. But the trap in that is saying there's a single cause for climate every place when you have dozens of different climates and they're not correlated with each other. So the question of what causes it, in a sense, is nature. That is to say, you're geophysicists. You have reversals of the magnetic field. What caused it? It's just autonomous. You know, the Dead Sea overturns every 60 years. What caused it? It's part of its nature. Caused it. So asking the question, if this didn't cause it, what caused it, assumes tons of stuff, including the fact that that metric that I showed you was climate. But it's not. I don't know if your wife will accept that, but
I work it out. So, one more question, Professor. Should we really be afraid of the Gulf current?
The what?
Of the Gulf current, the North Atlantic current weakening? In Europe especially.
You know,
how is it?
I think the answer is no, and there are two reasons I would say that. First of all, Europe, much of Europe has a mild climate, not because of the Gulf Stream. Gulf Stream pretty much peters out around Iceland. It is a mild climate because it's near a west coast. And the heat capacity of the ocean is much greater than of land. So for instance, Juneau, Alaska has a much milder climate than Boston because it's a west coast. Much of Europe, France, England, and so on, have a milder climate than the east coast of the United States because the ocean does not change as much as the land. If you are in the east coast of a continent, then the land with its low heat capacity changes a great deal. The prevailing winds are from west to east, and you are hit by the winds that have, the temperatures that have changed in the Midwest. California is hit by the changes that occur in the Pacific Ocean, and much smaller.
And one other thing, I'm very curious as to what effects does then CO2 have on the planet?
Health?
CO2. The CO2 must have some effects on the planet because it...
Oh, sure. CO2 has one effect that is well established. It is plant food. So we know that the increase in CO2 over the last 50 years has led to approximately 14-15% increase in agricultural productivity. That, of course, is something terrible because it means people will have more to eat and probably causes weight gain. But I mean, Let's be sensible. I mean, you can pile up things that you can worry about, but CO2 is nearly saturated. Remember, it's not, in other words, do you know what saturation means?
Yes.
Essentially, if you look at any radiative gas, it's like paint. So, for instance, if I take a window and put black paint on it, the first coat of paint stops a lot of light. The next coat of paint does much less. By the time I put on a third coat, it does nothing. This is the same thing with CO2. CO2, by the time you have, and we've never been there, 50, 60 parts per million volume, has already gotten pretty saturated. And now each doubling does the same thing. That's a particular regime you're in. So, for instance, you can calculate, it's an easy calculate. Let's say you went to net zero. Let's say the whole Earth went to net zero in 2050. This would cost trillions of dollars, much disruption, deindustrialization of the West. How much temperature would you have avoided if the whole Earth did it? It's about 0.6 degrees. So it's not zero, but it's awfully small. And if you are to consider cost-benefit, the cost-benefit is about infinite.
But then why isn't the narrative that the planet is cooling? Because
Pardon me?
why isn't the narrative that propaganda is that the planet is cooling? That would be much
Money.
No, but that would make much more money, because then that would mean that we must build more power.
First of all, one of the things that you should know, and I have this in the other lecture I give, this was a small community in 1988. Most of the world did not have climate research. You did not have great climate scientists from Zimbabwe and Uganda and so on, as you have today, allegedly. It was a small subject, and almost every leading figure in the field did not agree when Newsweek told you all scientists agree. And so it depended on people believing that headline rather than reading what people were saying. And you're following that. You're saying, well, if all these people agree, have you checked whether they agreed? No. And if you did check, you would see there was, one document which a former Hungarian Edward Teller initiated had almost 30,000 signatures of scientists with advanced degrees said this made no sense to them. I mean, you've been victimized by a propaganda campaign, and the propaganda campaign is motivated by the fact that the energy sector is the one sector which involves trillions of dollars. And that turns out to be crucial.
But taxes for them have been increased significantly because of climate change, for carbon taxes.
No, wait a minute. Climate change? I mean, right now you have the quote impacts, right? You have every weather event gives you a visual on television, and they say, see what climate has done. But that's not climate, that's weather.
Yeah. I'm saying that's what politicians use to justify carbon taxes that hurt energy.
Oh, sure. They use it for carbon tax. They give away trillions. The people who get the trillions give back 1 or 2% to the politicians. All of it's a nice system, but it's not good for people. It's not good for society. You already have in Sri Lanka, as you know, overturning a government because people were starving, because they used climate to get rid of fertilizer, because they said it was giving you N2O.
Thank you very much for the nice talk. It was very, very interesting, and I have one question. I don't know exactly how I can say it in a good way, because the global warming, or that we feel that this winter is not like in my childhood. Indeed, we have 18 degrees outside, we can feel it. It's one thing, but the other thing that we heard about also in the news, and we experience it in every year, that the weather, not the climate, but the weather became more extreme. I mean that we have larger mesoscale systems. We can observe tornadoes also in Europe, but it's quite rare here, or it was rare before. And and do you have any information from the literature?
Yes.
Previously, when the weather was warmer, it was accompanied by more extreme weather situation like right now?
Okay, the UN provides that. The Working Group 1 report, through the first 6 or 7 reports, always found zero correlation between these events and CO2.
Okay.
Now, the interesting thing is, as you have noticed, for many years, the picture of the global mean temperature anomaly was used to represent climate. And the political system realized this actually was losing impact. People were saying, what are you talking about? So they switched to impacts, weather. So today, I don't know if it's true in Hungary, but in the US, if there is something extreme, which there is every day someplace, we have a picture of it on the television screen, and that has an emotional impact. And so they're using that to say, look at what climate has done. You have that most recently with the California fires. And so the Intergovernmental Panel on Climate Change looked at the correlation of such events, and they couldn't find one.
You mean not find correlation between the warming itself?
Yeah,
and the
for instance, I'll give you an example. The Gulf Coast of the US, Alabama, Louisiana, and so on, have been cooling since 1940. If you take a survey of people in Louisiana or Alabama and say, what has happened in the last 80 years, 90 years, they will say it's warmed. The records show it's cooled. The area around Tallahassee used to be citrus agriculture. It's too cold for it now. But you told people it's getting warmer, and they will all tell you it's gotten warmer.
Okay, I understand.
Yeah.
I understand it's about the feeling, but what about the data? If
The data, what I'm saying is the data shows no correlation.
Okay, and it's cooling, and it means that there are less extreme thunderstorms and less extreme weather situation over there in those places where
Just go to the record. Go to the records. They're in the Working Group 1 report.
Okay.
They don't find a correlation.
Okay. So we have this more extreme weather situation.
Yes, we showed this, that if you look over the 30-year variations and longer, actually the bias is toward more of the stations actually cooling. If you look at the Köppen classification, all these different, they go differently. Each of the regions has different features. It's not as though the whole world has behaved in unison. It hasn't.
Yeah. Thank you very much for the talk. I'd like to ask your opinion about the extent human activity contributes to the feelable or the changes we can experience.
The only one I can think of is land use. In other words, when you build a city, that changes the climate of that area. If you build an airport, it changes the climate of that area. If you change the agricultural use, you change climate a little bit. Other than that, the human impact on climate seems to have been fairly small. You have attempts to, the business of the energy sector represented a major change in the green movement. So, for instance, before 1970, the ecological movement was concerned with species diversity, the welfare of whales, all sorts of things like that. There was also this concern with population, which was a little bit strange. 1970, a big change occurred in the green movement. The focus became the energy sector over everything else. But nobody quite knew what to make. So at first it was global cooling, because that metric was cooling between 1940 or 38 and 1975. And then it stopped, and then the Germans came up with the forest death due to sulfates from coal burning. And again, the forests recovered, so that ended. But, so far the attempts to find something from our energy sector, our emissions and so on, that change the climate has been pretty weak. The main thing that has occurred, and I think that's beneficial, the quality of air in many cities is better. But that's a health issue.
It's just worse. Sorry.
Pardon me? Yeah. I mean, in America, you had places like Pittsburgh, you had the killer fog in London, you had all sorts of things going on because of energy and essentially dirty coal burning. And we've improved that.
Thank you. May I have another question?
Sure.
You mentioned negative feedbacks, which works against global warming or at least the climate change in general.
They are mainly for the tropic. Remember, these feedbacks are only relevant to the tropics. They don't affect, they affect the rest of the world, but only by as much as occurs in the tropics. And so they're small. Cloud cover. What sort of percentage difference do they make to the radiating budget? 5%, 10%, 3%, all over the place. They're much bigger than CO2.
Well, actually, we have recently heard a presentation, a talk, in which it was argued that the warming which we experience recently is primarily due to the reduced albedo of the Earth, which is lower, the albedo is lower due to the reduced...
all these things may be possible. What we found was in the tropics, when you had warmer temperatures, you had less upper level clouds. We call that the iris effect. And that, has been around for 25 years. When we first published it was out of NASA. There were literally 20 articles immediately published criticizing it. And none of them held up. But it was, let's get rid of it. Here's the evidence feedback. And listen, MIT actually has a colleague who's in this paper who works on atmospheric electricity. Yes, that will you. Okay, yeah. He's fairly skeptical of this as well. I don't think that's going to play a major role in the issue. I mean, thunderstorms have their own characteristics, but who knows? I mean, I'm not arguing against looking for things. Of course, one should. But all I'm saying is, if you look at the data, you don't find polar amplification. You don't find that you have major changes. If you look at the data, it's much less than the models are saying should have occurred already. There is a bias in the models, and moreover, there is ample evidence that this whole issue was always political, and that the scientists were just dragged along. And then you have the issue of propaganda, constant repetition, tons of things wrong. And you have, in America, I don't know how it is in Hungary, you have the big problem that for now 30 years, 40 years, children have been told in kindergarten already the world is coming to an end. And you now have psychiatric disorders among children who are saying we have no future. In a normal world, you would call that child abuse. But we have now people who've grown up under that and been told this is the natural way to think about things. And, I'm always puzzled because, whatever views I may have, and I may disagree with the UN's IPCC, but even they don't say these things. So where do they come from? And I know where they come from. I mean, you see people desperate for acceptance of the end of the world. It's kind of a religious belief, and unfortunately it's associated with huge expenditures. I mean, if you look, for instance, in America, one of the last things that President Biden did was the so-called Inflation Reduction Act, which had nothing to do with inflation or reduction or anything else. It was actually supplying $9 trillion for climate-related issues. That is insane. On the other hand, if a government is giving out $9 trillion, there are plenty of people who will say, I'll take it. And the usual, I don't know how politics runs in Hungary, but in America, whoever takes the money, all they have to do is give back 1 or 2%, and the politician is happy. No.
So, Professor, in this age, against all this propaganda, what advice do you have for scientists who doesn't want to go with the flow? How can they publish papers if their questions are always well?
If you look, there was a release of the emails from East Anglia. This was about 10 years ago. And they were making it clear that you don't let people publish anything that contradicts this. So, for instance, my experience was it was difficult to publish, but I actually did, because, had a long-standing reputation. I published a couple of papers in the Bulletin of the American Meteorological Society. In each case, the editor was immediately fired. I mean, this is nasty business going on. Department of Energy and NSF tried to continue funding people, but the one thing that may occur, and I hope it does, is in the US, when there are major policy issues with defense or anything else, they have what they call a red team, blue team exercise. And this simply means you have people study both sides of the issue and argue it out to see if there's any reason to take one side or the other. We have never had that for climate except once. And that was the American Physical Society did it. And that was the reason that Steve Koonin switched sides. He was in charge of that, and it was clear there was no issue to support. But Trump was supposed to do that in his first term, and his advisors said, don't do it now, wait until your second term. He didn't get a second term immediately, now has it. I hope he runs this red team, blue team exercise, and the results of that will be the results of that. It's served well for other questions, and we need it for this one. I mean, it's already reaching the point where there is a ton of data that just absolutely opposes the scenario that's presented. And, the whole business of switching to weather events as proof of climate, that immediately shows a kind of desperation. So I think it's time to straighten it out.
Can I ask just one more thing?
Sure.
So, if they are so good at propaganda that literally almost everyone.
It's not just propaganda. There is punishment. There is funding.
But then why are they so bad at it that the Green parties in the European Parliament lost half of their seats in the last election?
Yeah. Oh, I think people are waking up.
But shouldn't they be good at propaganda so they win elections?
Well, the Green movement has its own peculiarities. We do not have a Green Party in the US. There is one, but it's tiny. In Germany, it was an important factor. But it was very much, I would point out, from the 68ers. And again, this is something before you were born, probably. But there were, huge amounts of student uprisings and so on, especially in the US, but also in Germany and France. This is when de Gaulle was overthrown. You had Red Rudy in Germany, which was violent. You had violent groups in the US. These people were still around trying to change society. And in many ways, they succeeded. But, the question that this gentleman asked, is there a correction? I think there will be.
Okay. Yeah, so I think another question. And in the meantime, I would like to ask the online participants if they have a question. Would they be so kind as to raise their hand?
Sure.
Just key it into the chat window and then we see it. But in the meantime, please carry on.
Sure.
My question would be, what is your opinion about the tendency in hydrologic cycle, maybe in Hungary? The general tendency from measurements, wet will be wetter, dry will be drier. And here in
Please
Hungary,
speak slowly.
wet will be wetter, or wet became wetter, dry became drier. And no, in Hungary, in the Carpathian Basin, we, in the last decades, the dry became drier situation. And it's very crucial.
Okay, do you mean by drier periods of drought?
Yes, maybe the mean discharges of rivers decreased half of the 40 years ago.
I wonder what I've noticed, and this is not my area of expertise, but have you studied the variance over the whole record?
Mm-hmm.
And you're saying that the variance has never been as large as it is now.
Mm-hmm.
Has there ever been a change in the data taking?
We are not a longer record than 100 years. In case of big rivers, for small, we have only some decades.
Do you have any, what would you call it? I mean, one of the things that is used that this guy Hubert Lamb used was church records of prayers said for different events and problems and so on. And that's how they concluded that the medieval period was milder, warmer. I don't know, I mean, these changes have occurred. There was a medieval period. If the people who are arguing that this was not global are correct, that's reasonable, also possible that you have local changes that are different. I know the claim has been made that you have more droughts and more floods due to global warming, but that's simply these same models. It's not from data that fail on every other ground. So, it could occur. I can't argue that, you haven't seen that. These things happen, but I doubt it's global.
Mm-hmm. Yeah, it's local. It's not global.
I mean, you've had that in the US. We were talking about urbanization. There's no question that building a city changes the climate.
Yeah. Thank you.
Another question, Joshua.
So just to confirm that I understood your point, right? You're saying that the data upon which the charts are made and the warming maps are produced is unreliable.
No, on the contrary, I'm saying the index they use, the global mean temperature anomaly, they show everybody analyzing it gets roughly the same thing. They get 1 degree warming over the last 150 years. And nobody's arguing that. I'm saying if you look at the data that went into that, it's all over the place. And some places are cooling, and some places are warming, and so on, over that time scale.
So basically, what we experience now, because we do experience change of climate, it is fairly local, regional, and it can be similar to medieval.
Yeah, it could be. As I say, we're talking about small changes. So the first thing I would say is, I don't personally notice if a day is 1 degree warmer or cooler. And I don't think you do. I don't think anyone does. Because it's small compared to the change over the course of the day. Yeah, if I look at the forecast for the next week, it looks a little bit warmer than average. And then a week from now, they're predicting it'll be much colder. And then every day, every week, every year, you deal with that. But you'd have to, we showed you on this, if you could look at the data over any record, the models don't agree with the data. And we're basing all these conclusions on models that are all over the place, but only in one direction. There's something wrong. So on the Zoom,
Yeah,
there's
on
no chat.
the Zoom I'm also checking, but I don't see any hands up or any message in the chat window. So I think in this case, yeah, no one.
Sorry. Professor, do you think that these one-dimensional or zero-dimensional radiative models can have any success with explaining the climate change?
No. I
Why
mean,
not?
okay. First of all, if it's one-dimensional, how do you account for the difference between the extratropics and the tropics? I mean, it's, it's again, you have models. I mean, in a way, it's hard for me to deal with the question. Here I have the Earth, here is the picture of the potential vorticity and the potential temperature, and it's all over the place and it's varying, and somebody said, can I approximate this with a one-dimensional model? The answer is no. And moreover, the physics changes dramatically according to the vertical component of the Coriolis force. How do I put that in a 1D model? So yeah, you're right. I mean, where did the 1D models come from? And they actually have a long history. They began with people like Schwarzschild in the beginning of the 20th century. They were astronomers. And yes, for their purposes, if you want to compare Venus and Mercury and Mars with the Earth, one dimension is adequate. Because if you look at the climate of the Earth, what you have is a picture where the tropics are reasonably constant. As far as we can tell, they've been constant for billions of years. And there's a temperature difference between the tropics and the pole that's been varying. Well, the variation, as we saw, didn't make a big change to the global mean temperature anomaly. So the anchor in the tropics, from an astronomical point of view, is the temperature of the Earth, plus or minus 5 degrees centigrade. And so if I'm comparing different planets, one dimension is fine.
Thanks, Professor Lindzen. So I think I will close now the discussion because we don't have any more online questions. And thank you so much again for your lecture and the very good answers. And I just would like to add as a personal remark, and I quote Descartes here, that I doubt everything except that I doubt myself. So it's a very important thing in science, and I think this is the mission of science, to give room for discussion, even if there are sort of clear contradiction in something. And this conversation and this communication was a good example of that. So in science, it's not the main aim who is right or wrong, but we are collectively searching for a better model or a better solution. Yeah. And this was a very good example of
look, essentially, whenever you hear that the science is settled, I mean, you have areas that are vastly more precise than climate, where nobody would accept that it's settled. And suddenly you take a field involving turbulent fluids, which you've never fully understood, and you said the science is settled. That very phrase should have told you something is wrong here. And instead, people said, the science is settled. You have to have resistance to that notion.
Yeah. Thanks, Professor Lindzen, and it's just a motivation for us and also for the future generation of scientists that never be shy to stand up if you think that your data and your measurements are right, even if you are going against the mainstream, even if it should be a motivation for you.
To be fair.
Yeah,
To be fair,
exactly.
even with my students, I've told them stay out of this area. No, I mean, it's not fair. I could not tell a student to take my position because they would pay too heavy a price. And the only fair thing for them to do is work on other things. But that is not a healthy state for the science.
Thank you
Okay.
so much, Professor Lindzen, for this excellent conclusion. And I also would like to thank for your participation. And Professor Lindzen will continue his lecture series in Budapest. So
With one that has nothing to do with the science.
but luckily we also can touch a little bit on the science. So we really thank you again so much for coming to our institute and for this lecture. And we wish you a very pleasant and useful journey here in Hungary.
You've already provided me with a view of a city I didn't know about, Sopron. It's a lovely place. Okay.
Yeah. So thank you so much again.